In this video, we are changing pace. We're going from the universal. We've seen the universal Lie algebra before. We're going to be looking here at the free Lie algebra. Free Lie algebras. I think it's related. I don't know exactly though. I guess the whole point of this series is I'm learning at the same speed as the people watching this, right? So, quick note. Throughout, K is a non-zero commutative ring. We are switching bucks again, it's worth noting too, so the notation is going to be a bit different. With a unit, just 1. And everything is over K. Everything is over K, unless noted. So, we're going to start out talking about the enveloping, not the enveloping algebra, but the enveloping bigebra of a Lie algebra. And throughout this, let G be a Lie algebra over K, of course. With enveloping algebra U and canonical mapping sigma and canonical filtration of UN, where n is a non-negative integer, of course. So we're going to start looking at primitive elements of a cogebra. Okay, quick note before we do that. What is a cogebra? Because they kind of assume here you're going to know it. So I'm going to do another quick, side introduction to the topic as soon as my resource on it loads. So the cogebra is of course going to be the categorical dual. Cogebras are the dual of algebras. So a cogebra is a module, I guess. A module C over K with K linear maps this is not the base of a root system, this is a function saying an element C into the tensor product with C and C, and a function epsilon setting C into K, such that the following diagrams commute. And we have two diagrams here. The first is we start with C. We're going to take its this triangle map, and this will help us understand what these things that we're dealing with here are. And this here, we're taking the triangle on the left. This, we're taking it on the right. In either case, we're getting the triple element. And secondly, we have, once again, we're taking the triangle map twice. And this time, we're applying this function epsilon to the left or the right. And this gives us, on the left, this one I'll give it isomorphism of the base field with our module, which is isomorphic to the module, which is isomorphic to the module times the base field on the other side. And then this gives us a map from C to C, which is going to just be the identity. So we can write this here as the C identity tensor, the triangle map with the triangle map is equal to we can do it on either side. And here we get that the composition of the identity with this epsilon map with triangle map on either side gives us the identity. Now, if we invert these diagrams, let's look at the duals of these diagrams. I'm not going to write the functions. You have to keep track of what's going on there, but this should be pretty clear. We have some dual function triangle sending C tensor C into C. And we see this is the associativity of multiplication. And multiplication is a map from the tensor of C and C into C, meaning that it's going to be a bilinear function, which multiplication is. And the dual of this map, if that C is getting sent into C tensor C, this is not an official symbol, but I'll use like tildes to represent the inverses, I guess, because it'll make it clearer what's going on here. So we see that this triangle, the dual to triangle, is just the inverse of multiplication. And they're going to use different symbols for in Bourbaki, so we're going to have to adapt to that. And we get this function taking the dual of the above, where this is like the dual of E with the identity on either side, and this is our multiplication we've seen. So this is giving us the existence of the unit. Because keep in mind, what this is saying is we can express an element, like this diagonal map on the right is saying that the top left and bottom right corners of this diagram are the same spot, essentially. So it's saying that we can pair any element in our C with some element which doesn't matter what side it goes on, that will make it kind of just the identity. So we see this is multiplication, and this is the function which essentially is going to map into whatever the equivalent in C whatever the unit element is in C that's acting as a unit for multiplication, and scaling that up appropriately. So which means our maps here, triangle and E, are essentially going to be acting categorically as the opposite of the unit and of multiplication. So that's the general idea of what a cogebra is. Now let's look at Bourbaki notation. Back to the official text. To the official text. So we are considering a cogebra E with coproduct sending, this is the dual to our product, and co-unit E, which here is being described as a linear form on the key, linear form on E as a key module, such that the identity of E is, this is the maps we saw before, where we can essentially unmultiply the identity with this co-unit. You can co-multiply it with a co-unit, I guess would be the more official way of describing it. And keep in mind, so I think E is a map from, must be a map from E into K. Now we're going to let E plus be the kernel of this co-unit. And we're going to pick an element U in E such that the co-multiplication, the coproduct of U is just a tensor product of U with itself, and the co-unit of U is 1. Then E as a key module is the direct sum of our E positive and the submodule K times U, which is free with basis U. Let the projectors of this decomposition be pi U sending E into the kernel of the co-unit, and eta U sending E into a multiple of the unit. Then we have that pi U of some x is equal to x minus whatever the image of whatever the co-unit of x is acting on u, and eta u of x is just epsilon of x, the co-unit of x, scaling u. This brings us to our first definition, where an element x of E is called U primitive. If the co-unit of x is x times u plus u times x. Such elements form a submodule of E, which we denote as the primitive submodule generated by U of E. Now let's look at a proposition. That every U primitive x of E is in E plus, which reminder means that it has a co-unit of 0. And the proof from the definition of U primitive, we have that x is equal to epsilon x dot u acting on u plus epsilon u acting on x, which is going to be epsilon x acting on u plus epsilon u we know is 1, so that's just going to be x. So subtracting x from both sides, we get that epsilon of x acting on u. Epsilon x just has to be 0. And it comes with a remark. That if x is an E and the co-unit of x is equal to x prime tensor u plus u tensor x double prime, for x prime and x double prime in being in the kernel of the co-unit, then we have that x is equal to the unit of x prime, the co-unit of x prime acting on u plus the co-unit of u acting on x double prime, which is going to just end up being x double prime. Similarly to the above, x is just going to then be x prime, and x is u primitive. Now, for all x in E plus, we're going to write cu positive of x to be c of x minus essentially minus x tensor u minus u tensor x. which comes to our next proposition. Which states that the projection of u into the kernel of the counit on both sides of the coproduct is equal to this new map Cu positive acting on the elements in the kernel of the counit. It's a lot to keep track of here, and my brain is flying. For x and e, we get that. I'm just going to make this be its own line. Pi u tensor pi u of c of x is equal to, well, we know that pi u is 1 minus eta u, because they're like alternative, they're co-projections. I don't think that's the right term, but you know what I mean. So this gives us expanding, foiling, you get cx minus 1 tensor eta u cx minus eta u tensor 1 of cx plus eta u tensor eta u of c of x Since epsilon is the counit of E, we get that 1 tensor the projection eta u of c of x is just going to give us x tensor u, and similarly applying eta u to the other side of c of x is going to give us u tensor x. So our eta u tensor eta u of c of x is going to be equal to eta u tensor 1 of 1 tensor eta u of c of x, which is going to be eta x on u tensor u so pi u tensor pi u of c of x is then just using our first formula and just expanding to what each one is. 1 tensor eta u of c of x is x tensor u. Similarly, eta u tensor 1 of c of x is u tensor x. And plus eta u tensor eta u of c of x is eta x of u tensor u. Also, we have that cu positive of pi u of x is also expands to work out to be the same thing. That's our proof. Now, as the kernel of the counit is a direct factor submodule, direct factor submodule of E, the tensor product of E plus and E plus can be identified with a direct factor submodule of E tensor E. As under this identification, the tensor of pi u tensor with pi u projects E tensor E onto E positive tensor E positive. By the previous proposition, Cu positive maps E positive into the tensor of E positive with itself, and so pi of u is a morphism of the cogebra EC into the cogebra of E positive with Cu positive. Alright, and this comes with a proposition and a lemma. Our proposition now if our EC cogebra is co-associative or alternatively co-commutative, which I think when I gave the external definition of a cogebra way back up here, I think this diagram on the left assumes that multiplication of the algebra is associative, which isn't necessarily true in general. It just helps motivate that definition a bit more. And I think also you can see how you're going to define co-commutativity in the same way. And so if EC is co-associative, co-commutative, so is this cogebra of E positive C plus U prime. And this comes from a lemma. Let pi from E to E prime be a surjective cogebra morphism if E is co-associative or co-commutative. Co-associative, co-commutative, so is E prime. And the proof, let B be an associative K-algebra oh man. The Mapping of f into the composition of f with pi is an injective algebra homomorphism of the k homomorphisms of E prime to B into the k homomorphisms of E into B, and then the result is known. So that's always a cool thing to be rating. We're a bit short. One thing I will say, scratch notes. My guess, this is my guess, co-commutativity. I kind of just want to like write out the diagrams. So commutativity, you have this function k, we have this space k tensor k, right? Commutativity is that you can swap the order of multiplication. So if we write this as, say, beta, where beta is the swapping, this is going to be multiplication, this is going to be multiplication into k, and then this is just the identity, meaning these are the same, where beta of x and y is y and x. Co-commutativity, we then reverse all the arrows. And I guess these maps both beta and the identity are symmetric bijections equal to their own inverses, so like that. So in this case, it's going to be k, two copies of it the same way. We have the co-product into k tensor k, and I should check if I can find that this is right online. And similarly, we're going to have beta. I think that's what co-commutativity is going to be, is a triangle on both. It says on Wikipedia, it says here that co-commutativity is co-commutative if I was right on my function beta. Beta composed with delta is delta, which we have here. On the left we have the diagram that delta is equal to, the multiplication is the same thing as multiplying it by, and then on the swapping. And here in my diagram we have that delta is the same thing as on multiplying and then swapping, so I am right. So I did successfully guess what the co-commutativity was, and I don't want to keep on with the book because I'm tired and it's the end of the day, so I'm going to read a bit off of a external source. So I'm going to write here dubious quality. This should all be right, but this is from a less trustworthy source. So all these keys should be C's, I guess. That is one thing, because we're using the notation where C is our cogebra and not whatever it is above. Don't you love switching letters all the time? It says that here. A linear subspace I in C is called a coideal if I lies within the kernel of the counit, which we saw above, and the delta of I lies within I tensor C plus C tensor I. With such, C over I is a cogebra in the typical manner. A subspace D of C is a subcogebra if the inverse product, if it's closed under the opposite of, if it's closed under co-multiplication, essentially. We have that if f from C1 to C2 is a cogebra morphism, the kernel of f is a coideal in C1, and the image of f is a subcogebra in C2. And we have the isomorphism theorems, and there's other concepts in that which we're going to get into next time. I think I gotta kind of call it here because this is getting a little dense, and we're close enough to our time limit that if we go to our next chapter, we're going to go way over time. So yeah, thanks for watching.